The project for our IRE course is integrating network and community detection discovery for planning constant and outline nodes. What we so basically what happens is we want to do is community detection and on the given network. But what usually happens is that the network is way too large to do the whole thing on the complete network. So what usually people prefer is they take part of the network and perform community detection on that part. But this is not usually helpful as it this is not usually helpful. So what we so what our aim in this project is to incorporate network discovery and community detection in the same algorithm. And yeah, no, but when we talk about graphs, what usually happens is the graph is sometimes way too large for us to get the whole graph, or maybe it's even possible that it's not even the whole graph is not even accessible, or way too expensive to discover nodes. Like consider terrace networks, or Facebook profiles, or the general data that we have. It's not possible for us to get the complete graph anyhow. So it does make sense to incorporate both the parts in the same algorithm. Since the quality of mining process will obviously depend upon network discovery, we try and incorporate those two together. By this discussion, we can easily conclude that these two parts are mutually dependent and are necessary to enhance each other. So now consider this example. The black nodes are the nodes that we know till now, and we wish to add a new node to the graph. It can the black nodes represents the nodes that are known till now, and gray ones are the ones that are not known. It can be easily seen that node 1, 2, 3, and 4 are the candidate nodes. Node 2 and 4 should not be considered to be added to the graph as the degree is not high. Node 1 and 3 are the remaining candidates. Now, what happens when we add node 1? Basically, the two communities that we have till now will become more connected. This is not helpful as in later on we'll obviously need to distinguish these two, and hence node number 3 is helpful as it strengthens the community A, as well as helps in distinguishing community A and from community B. So from this discussion, we can conclude that the following parameters are required in our nodes. It should be there should be high parity, large observed degree, and balanced communities. By what I mean by high parity is that it is better for the neighborhood of a node belonging to the same partition. This tends to help that community to be more dense and push the center of that community far apart from the other communities. What I mean by large observed degree is that it usually helpful when the node that's being added has high degree. Uh, it helps us to increase the visible network of the given graph, and we also want our communities to be balanced. If we don't accomplish that, then one community will tend to become larger and dominate the others, and it might result all the communities to merge together. So now we try and define our problem statement. GNA is our graph where N is a set of nodes and A is the set of edges. Now GS represents our starting graph. NS and AS and QS represents the starting nodes, the starting set of edges, and the starting cost of each node respectively. Now, what usually happens is all we know about the graph is the set of target nodes. We wish to conclude the community of these target nodes. So it makes sense to start make NS equal to N. This is the broad framework of this approach. We start by initializing the parameters, and we iteratively find a node and updates its community until our budget is reached. So this is the approach we use for choosing the new node. We basically compute score for each node that's in the feasible region. The feasible nodes are depicted by NC minus S. That is the nodes that are still visible but are not queried so far. And then the score is adjusted by some parameter. This is how the scores are being computed. There are two parameters to do that. One is normalized cut and other is modularity. We try and normalize the score by multiplying it by its costs. The higher the cost, the more chances of it not being selected. Now what we want to do is discover the community of each node. We start by assuming that the nodes have a poised distribution. Uh, we we introduce a few parameters. Theta ik represents the propensity of a node I to have edges to community k. So we introduce another dummy variable named qm. We follow an EM algorithm and update these two parameters so as to know the final communities of each node, and that is basically given by argmass of theta ik, and that's our project for IRE.